In today's lecture, we are going to start very important topic, that is sliding mode control. This sliding mode control, that is actually very powerful technique, and it can be utilized to design controllers for nonlinear systems. One of the advantage of this approach is that this approach is robust against uncertainties. Later on, we shall talk about matched uncertainties and unmatched uncertainties. So this technique is actually robust against matched uncertainties. We shall talk about matched uncertainties. Another very important advantage of this approach is that the implementation of this controller is very simple. We have already designed controllers using feedback linearization techniques, and later on we shall also study backstepping approach, and we shall see that this approach, the controller finally that you get, that is much simpler as far as implementation of the controller is concerned. There is one disadvantage of this approach, and that is this approach is associated with chattering. What is chattering? Chattering is vibrations or oscillations in the control action as well as in the variable that is being controlled. We shall talk about this effect in more details, and fortunately this chattering effect that can be either completely eliminated, or at least it can be reduced in magnitude so as to reduce the adverse effects of this chattering. Therefore, this makes this approach a very powerful approach. We shall learn the concept of this sliding mode control by taking relatively simpler systems, and then we shall extend the approach to more complex systems. So the system that we are going to start with, that is a simple system. We are talking about second order system which has only two states. Later we shall extend the approach to more general class of nonlinear systems. Here h of x and g of x are some nonlinear functions of the state variables. Furthermore, these h of x and g of x, these can be uncertain. So g of x and h of x, these can be uncertain, and these can be some nonlinear functions as well. There is one assumption, and assumption is that g of x, this thing which is being multiplied with the control input, this nonlinear function is always positive. That is, it is greater than or equal to some constant, and this constant is greater than 0. So that is, this g of x is always positive. To design a sliding mode controller for this nonlinear system, we define a surface. This surface is defined by this equation. A x1 plus x2 is equal to 0, and we rename this to be equal to S. What is this equation? A x1 plus x2 equal to 0. This is equation of a straight line. It is equation of a straight line. So for a system with two states, this is equation of a straight line. And if we have equation with three variables, then that will be equation of a surface. And if we have a higher dimensional system with more number of states, then this will be equation of a hypersurface. So in general, we call this a sliding surface, a surface, right? This here it is simply equation of a line, but in general we call it a surface and call this equation sliding surface. So if we can somehow maintain system trajectories on this sliding surface, this has very useful consequences. That is, if we can somehow ensure s equal to 0, then what does that mean? From this equation we see that s equal to 0 implies that x2 is equal to minus ax1. And from this first equation we have x1 dot is equal to x2 and x2 is equal to minus ax1. Therefore x1 dot is equal to minus ax1. So if we can somehow ensure this thing s equal to 0, that means this thing x1 dot is equal to minus ax1. And what is solution to this first order differential equation? Right, you all remember the solution to this differential equation is given by this expression. Since we have taken a to be a positive constant, so this will be a decaying exponential, and that is the this state will converge to the origin. And what about second state, x2? x2 is simply related with x1 by this expression. So x2 will be simply a scaled version of x1 that is given over here. x2 is equal to minus a x1 of t. So what does that mean? If we can somehow ensure s equal to 0, then system trajectories will converge to the equilibrium point at origin, that is the system is stable. And furthermore, there is another very important point. The system is entirely described by this differential equation. The second differential equation is even not required. You can even find x2 without this second differential equation. Only this differential equation is required. That is, the system is now described by a lower dimensional system. The dimension of the system is reduced. So here is the summary of the discussion that we have made up to this point. On the sliding surface, that is when this equation is satisfied, the system is described by reduced order dynamics. We had two differential equations originally, but when this equation is satisfied, that is on the sliding surface, the system is entirely described by this differential equation, one first order differential equation. So the system is described by reduced order dynamics. The states also converge asymptotically to the equilibrium point. That is obvious from this expression for x1 and x2. So x1 is exponentially decaying and will finally converge to 0. And likewise x2 is also exponentially decreasing because it is simply some scalar multiple of x1. So states converge asymptotically on to the equilibrium point. We can also control the convergence rate by choosing appropriate value of this positive constant a. This positive constant, we have chosen this positive constant, we can change it to control the convergence rate. And furthermore, system dynamics are independent of g of x and h of x, because system is only described by this differential equation. Entire system is described by this differential equation, that is it is independent of g of x and h of x, which are uncertain, but it is independent of these uncertain nonlinear functions. So if we can ensure this equation, we can keep the trajectories on the sliding surface. We have these consequences, these good results. But now there are questions, that is how to bring the trajectories to the sliding surface. By bringing the trajectories to the sliding surface, we mean that how we can satisfy this equation. So how to bring the trajectories to the sliding surface? This is the first question. And second question is, once the trajectories are brought to the sliding surface, how to maintain the trajectories on the sliding surface. That is how to confine the trajectories to the sliding surface, how to keep on ensuring this equation. So the answer to these two questions, both of the questions, is over here, if we use this control law, this will bring any initial trajectory to the sliding surface in a finite time, and it will furthermore maintain the trajectories to the sliding surface. So once the trajectories are maintained on the sliding surface, then we have seen that the system dynamics will asymptotically converge to the equilibrium point, that is our objective. What is this control action? What is this signum function, SGN, signum of S? That is basically sine of S, and that is you are already familiar with this thing. Signum of S is equal to 1 if S is positive, it is equal to -1 if S is negative, and it is equal to 0 if S is equal to 0. And what is this beta? Beta is basically given by this expression. Beta of x is greater than or equal to rho of x plus beta naught, where beta naught is any positive constant greater than 0, any number which is greater than 0, and rho of x is given by this inequality. Rho of x is an upper bound on this expression, that is rho of x is greater than or equal to absolute value of this expression. G of x is this term which is being multiplied with u, and this h of x is this nonlinear function. So if we use this control law, what will it ensure? It will ensure that any initial condition is brought to the sliding surface, and furthermore it will ensure that trajectories are maintained on the sliding surface. And once the trajectories are on the sliding surface, the states will automatically converge to the equilibrium point, asymptotically converge to the equilibrium point. We have given this statement, and we need to prove this statement as well. We need to prove that this control law will bring the trajectories to the sliding surface and will maintain the trajectories on the sliding surface. And the proof is very simple. You have already studied the Lyapunov theory, and we can utilize the Lyapunov theory. S was given to be equal, S was equal to ax1 plus x2, and what will be the derivative of S with respect to time? S dot is equal to a x1 dot plus x2 dot, where x1 dot is equal to x2 and x2 dot is given over here. We simply substitute the expressions for x1 dot and x2 dot over here, and then we get an expression for S dot. This is dynamics of another system, and what we want to ensure, we want to prove. This is another dynamic system, and we want to prove that this S asymptotically converges to the equilibrium point, to the origin, S equal to 0. So how we can do that? The procedure is well known to you. We define a candidate Lyapunov function, and simplest choice for the candidate Lyapunov function is quadratic Lyapunov function, half s square, and we compute the derivative of this along system trajectories. V dot, the time derivative of this function v, that is equal to s into s dot, and s dot is given over here. We substitute. We have substituted this over here and split the expression into two terms. We know that every function is less than or equal to absolute value of that function. So therefore this function is less than or equal to the absolute value of this function. So absolute value of this function is written over here. Absolute value of s multiplied by absolute value of this expression. So therefore this term, this function is greater than or equal to this function. Therefore this sum is greater than or equal to this v dot. Obvious. And then from this relation, what is G? G is always positive. We know, we have this assumption, and therefore this ax2 plus h of x, ax2 plus h of x, that is always less than or equal to rho multiplied by g of x. G of x is always positive, therefore it can be taken outside this absolute value. So absolute value of ax2 plus h of x, that is always less than or equal to rho of x multiplied by g of x. So this is replaced over here, rho of x, g of x. And what we have done here, we have substituted this control action, that is u is equal to minus beta of x into signum of x, signum of s. What is s multiplied by signum of s? What is that? S multiplied by sine of s, that is equal to absolute value of s, right? S multiplied by sine of s, that is equal to absolute value of s, and this g of x is written as it is over here. And what is beta of x? Beta of s, beta of x, that is greater than or equal to this thing. So we have substituted here smaller term because it was negative sign over here. So this overall expression will be greater than or equal to this expression, because here we have substituted a smaller term. This beta of x is replaced with a smaller term because of this negative sign over here. So therefore this expression is greater than or equal to this expression, which is greater than or equal to v dot. If some terms are cancelled over here, this term is cancelled with absolute value of s, g of x, rho of x, and we are only left with this term beta naught multiplied by this expression with a negative sign. And what about g of x? We have assumed that this is always positive and it is greater than a positive constant g naught. So therefore we have this expression v dot is less than or equal to this expression, where beta naught is positive, g naught is positive, absolute value of any function is always positive. So what is conclusion? V dot is negative definite. And what does that mean? This s will asymptotically converge to equilibrium point at origin. What is meaning of asymptotic stability? It will take how much time for s to reach to 0? It will take infinite time for trajectories for s to converge to 0 if we use this control law, right? Any initial trajectories will converge to the sliding surface s equal to 0. That is, if s is initially not equal to 0, if we use this control law, s will finally converge to 0. Although by this analysis we have seen that it may take infinite time for the trajectories to converge to the sliding surface. However, we can furthermore ensure that it will take finite time for the trajectories to reach to the sliding surface. From this analysis, we have this conclusion, that is, as t tends to infinity, s will tend to 0. But we can prove that it will take finite time, and that proof is also not very difficult. All these things written from the previous slide. V is equal to half s square, and we have demonstrated that v dot will be less than 0. This expression has this meaning. V dot is actually nothing but dv by dt. And what is s? Absolute value of s is equal to 2 multiplied by this candidate Lyapunov function v square root. From this expression, we bring 2 to this side and take the square root. So absolute value of S is given over here, right? This thing can be further rearranged to write it in this way. What we have done is that we have brought this square root of v to this left hand side, and this is written in form of differentials that is given over here. What do we get if we take the integral of this inequality? Integral of this inequality is given over here, and this, what is this thing? This term is basically from here, and what is this thing? This is constant of integration. We have integrated this inequality and we get this expression. You can easily integrate it, all of you know the procedure. We have simply rearranged to write it in another format. We want to determine the time when s becomes equal to 0, that is s of t becomes equal to 0. So we want to determine that time. How we can determine that time? We have simply substituted s equal to 0. We want to determine the time when s becomes equal to 0, that is when the trajectories have reached to the sliding surface, and that time is less than or equal to this, that is given over here. So what is the meaning of this thing? How much time is required for the trajectories to reach to the sliding surface? It is finite number. S of 0, what is S of 0? S of 0 is equal to x1 of 0. By substituting the initial condition over here, we get S of 0. So that will be obviously some finite number, and the time required for the trajectories to reach to the sliding surface is also some finite time. So the conclusion, it will take finite time for any initial condition to reach to the sliding surface. Clear? That is, to summarize, we had taken this nonlinear function, we had defined some sliding surface where a is some positive constant, and by changing a we can control the convergence rate. We have also proved that this control law will bring any initial condition to the sliding surface, and we have already proved it, and it will also take finite time for the trajectories to reach to the sliding surface. We have also proved this thing as well, that is, it will take finite time for trajectories for any initial conditions to reach on the sliding surface. And what is behavior of the system on this sliding surface? On the sliding surface, the system is described by this differential equation, that is, system is described by reduced order dynamics, and on the sliding surface the system dynamics are also independent of uncertain nonlinear terms. And what about this control law? This control law requires an upper bound on rho of x. This we need this control law, there is a term beta which is an upper bound on rho of x, and rho of x is upper bound on these uncertain nonlinear functions. That is, control law is also independent of uncertainties, and therefore sliding mode control is robust against uncertainties in g of x and h of x. This upper bound on these nonlinearities, we have taken it rho of x. This upper bound can be even some constant, and if this rho of x is constant, then this controller, this beta of x will be a constant, and this control action will be even further simplified, and that is, you can have a very simple controller. There you can simply implement this controller by simple relay on-off controller. This is nothing but on-off controller. So that is the implementation of this sliding mode control is very simple. The idea of sliding mode control is graphically illustrated over here. Here you have this state space, x1 state on this x1 on this axis and x2 on this vertical axis. And what is this equation? This is equation of a line, straight line in this two-dimensional space. And what does this control law do is that if the trajectories are not on the sliding surface, for example, if initial conditions, these are the initial conditions, that is s is not equal to 0, if s is not equal to 0, what does this control law do? This control law brings any initial condition to this sliding surface. Once the trajectories are on the sliding surface, these will automatically converge to the equilibrium point. Is that clear? This control law will bring any initial condition to the sliding surface and will maintain the trajectories on the sliding surface. And on the sliding surface, the states are will converge asymptotically to the equilibrium point at origin. And on the sliding surface, the system dynamics are independent of nonlinear functions. Therefore, this approach is robust against uncertainties. The control law itself requires an upper bound on the uncertain functions. Therefore, control law is itself also robust. Is that clear? Corresponding to some other initial condition, for example, corresponding to these initial conditions, control law will also bring it to the sliding surface, and on the sliding surface the trajectories will automatically converge to the equilibrium point.